All right, I want to show you some applications of Gibbs functions. I'm going to show two examples. One is where we use the Gibbs function to calculate something called the adiabatic lapse rate. And that's the rate at which the temperature of a water parcel, seawater parcel, changes as you compress it. So if you compress a fluid parcel, then you're doing work on it and its temperature will go up. And conversely, if the fluid parcel expands, then it will cool. Because now it's doing work on the environment and energy goes out of it. So the reason this is important in the ocean is when fluid parcels move up and down, to first order, they don't mix with the environment, so they conserve their salts, their salinity, and also their entropy. And so when they'll move, their temperature, in situ temperature, will change without the internal energy changing other than the work done on it from compression. And another application is to derive the speed of sound in seawater from the Gibbs function. So I'll do those two examples, but before we do that, we have to review some math, and otherwise it's very complicated to do those derivations. So I want to review a little bit of linear algebra and some calculus, multivariate calculus, and then after that I will go back and do the thermodynamic applications. All right, so first a little bit of linear algebra. Okay, so suppose we have two vectors, v1 and v2. And this one has coordinates v11 and v21, and this one has coordinates v12, v22. Right? We can imagine taking this first vector, suppose this is the origin over here, and transporting it parallel to itself along v2. Right? If we did that, we would sweep out this area. Right? And the area of this parallelepiped is given by the determinant of the matrix whose columns are v1 and v2. So if I put v11 here and v21 there, so this is the v1 vector, and then the v2 vector over here, that's v12, v22, then what I get is the determinant, which is this times that minus this times that, v11, v22 minus v21, v12. And you can do a little bit of geometry, put in an x-axis and a y-axis and compute the area of the parallelepiped, right, with a little bit of geometry, finding these areas and the bigger area. And you can convince yourself that this is indeed the area. All right, one thing that's important to know about the determinant is it's not just the area, it's also the oriented area, in the sense that it has a sign. So the same way that you can have a vector of a given length, you can point it in opposite directions, change the sign. Same thing with the area. If we take a little parallelepiped and we look at it from one side, then that area is going to be positive. We look at it from the other side, it will be negative. And so this is reflected in the definition of the determinant, that if we interchange the two columns, so if we take the determinant of v2 and v1, we'll get the negative sign of what we have now, right? And you can see this. If I take the determinant of v2 first, v22, and then v1, v21, right? This is v2 and this is v1. And if I compute that, I get v12 times v21 minus v22 times v11, which is the negative of the previous one. So the second one, you can think of this as the area of sweeping v2 along v1. And if you sweep v2 along v1, you have a different orientation than if you sweep v1 along v2. And so you flip the sign. All right, so that's determinants in 2 dimensions. We can do the same thing in 3 dimensions. So let me show you how that works. Suppose now I have 3 vectors, v1, and now it has 3 components because I'm in 3 dimensions, v11, v21, v31. A second vector, v2, is equal to v12, v22, v32, and v3 equals v13, v23, v33. All right, so if I take the first 2 vectors, v1 and v2, and I sweep v1, v2 along, let me change the order, v2, v1. If I sweep v1 along v2, I'll sweep out this area, And now if I take this area and sweep it along V3, suppose V3 is over here, then I will move this area parallel to V3, or sorry, parallel to itself along V3, and I'll get this area, right? And I'll have swept out this volume over here. And the volume, the oriented volume of this shape, this prism, is given by the determinant of V1, V2, V3, right? You take those three vectors and you form a matrix, and then you get the determinant. So that's equal to the determinant of, now I'll put in the components for the matrix, V11, V21, V31, V12, V22, V32, V13, V23, V33. And the way we compute the determinant is the following. So we can expand along a row, any one row, or any one column, but the key thing is that the sign alternates. So it will be, this will be equal to V11, the first one, times this subdeterminant, where we've crossed out, if we take the 1/1th element, we cross out the first column and the first row. So we have V22, V32, V23, V33. Then we go to the next element. Suppose we're expanding along the row. Now we have to flip the sign first, V12, and then we take the subdeterminant by crossing out the first column, the middle column and the top row. And so that's V21, V31, V23, V33. And then the last one will be plus again, V13 times the subdeterminant by crossing out the last column and the first row, which is like running out of space, but V21, V22, V31, V32. All right, so you have these three small determinants, which you already know how to compute, right? It's this times this minus this times that, and then you multiply by that, minus this times this minus this times that times this one, plus V3, and then same thing. All right, and if you do that calculation, you'll get the volume. You can check that using some geometry, simple geometry, to convince yourself that indeed this is the right volume for this prism shape. The determinant has the same properties that if I interchange two columns, I flip the sign. Similarly, if I interchange two rows, I will flip the sign of it. All right, more properties of determinants. If I have two matrices, A, which is defined as A11, A12, A21, A22, and B, which is equal to B11, B12, B21, B22, I can compute the determinant of A, right? That's just A11, A22 minus A21, A12. And I can compute the determinant of B. That's B11, B22 minus B21, B12. And if I multiply those two together, or if I multiply the two matrices together, I get AB, right? Which is going to be, the first element will be this row multiplied by this column. So that'll be A11, B11 plus A12, B21. Then this row times this column for the second element, A11, B12 plus A12, B22. Then this row times this column to get this element, A21, B11 plus A22, B21. And finally, the lower one is the last row and the last column, A21, B12 plus A22, B22. And if I compute the determinant of this matrix, right, if you do the algebra, you'll see that that is indeed equal to what you might expect, determinant of A times the determinant of B. I'm not going to show the derivation, you can try it on your own. So that's another property, that the determinant of A, B, is the determinant of A times the determinant of B. So you can apply the determinant to each interval. So that's another property of determinants that we're going to use to do the thermodynamic relationships. All right, now a little bit of calculus involving those determinants. So maybe you've studied this before in your multivariate class, calculus class, but maybe you haven't, or maybe you can't remember, so I will review. And we've already used some of this result when we derived the volume element in spherical coordinates. But I'm going to do it again. First I'll do it in 2D where it's simple for polar coordinates. So suppose I'm trying to do an integral. So I'll do an example, and I think that will explain what I'm trying to do. So we're trying to do the integral, the indefinite integral of x squared plus y squared dx dy. And since there's a square root and there's squares, it looks kind of complicated. So one thing we can do is we can change this to a different coordinate system. Namely, this looks like the radius vector, so we'll change it to polar coordinates. So in polar coordinates, if I have y and x axis, and I have a point out here, right? This is the point xy, and this angle is theta, and this distance is r, and this is rx, sorry, x, this distance, x is equal to r cosine of theta, and then this distance here is r sine theta, and that's y. So the polar coordinates are x is equal to r cos theta, and y is equal to r sine theta. So we want to do a change of variables, right? If I substitute x for this in here and y for this in here, what I'll get is the integral of the square root. X squared is r squared cos squared theta plus y is r squared sine squared theta times dx dy. And then I can pull out the common factor of r squared out of the square root. So I get the integral of r. And then what I'm left on the inside is cos squared plus sine squared theta dx dy. And that is just equal to 1. So that's looking good. I have r dx dy. But the problem now is that my area element dx dy is in the wrong variables to do the integration. So I want to change this area element from coordinates x and y to the coordinates r and theta. And the formula to do that change variables is that d area in Cartesian is dx dy, and in polar it's going to be something times dr d theta. And you can know that it can't, you shouldn't see that it's not just going to be the r d theta, because they have different dimensions. This x is length, y is length, so this is an area. R has units of length, but theta is dimensionless. And so this is just a length. So we need a scaling factor out front. And that scaling factor is, we use this notation here, x, y, r, and theta. And this is called the determinant of the Jacobian matrix for the change in variables. So first, what's the Jacobian matrix? The Jacobian matrix, J, is, here will be dx, dr, dx, d theta, that's the first row, and then my second variable is y, that's dy, dr, and dy, d theta. All right, and if I take the determinant of this, right, determinant of this matrix, dx, dr, dx, d theta, dy, dr, dy, d theta, then I use this notation. This is the standard x, y, r, theta. So this notation with these partials, that is the change of, the Jacobian determinant for the change of variables from x and y variables to r theta variable. So I can calculate these derivatives, and I can evaluate that determinant. So dx dr, right, is just cos theta. Dx d theta is r sine theta with a minus, right? The derivative of cosine is minus sine. And then dy dr, that's r sine theta. Oh, sorry, just sine theta. And dy d theta is r cosine of theta. And I take the determinant of that, which I do by doing the cross product, or the product this times this minus this times that. And what I get is r cos squared theta minus makes it a plus, so plus r sine theta squared. So I get r cos theta squared plus sine theta squared, and which is just r. So the Jacobian determinant is just r. So this integral here, if I do the change of variables, let me erase all this mess here, becomes, this just evaluates to r, dr d theta. And so now I can finish my integral for the example. This becomes the integral of r times r dr d theta. I sound like a seal, r. So this is r squared, the integral dr d theta, which is now equal to 1/3 r cubed times theta. All right, so I can do the integral very easily. So the change of variables for the area element in polar coordinates is r dr d theta. You can kind of see that that's going to be correct. If I have a radius vector coming this way, right, this distance here is dr. This is the r direction. And this angle here is d theta. So this arc is r d theta, and so the area is going to be this times this, right? In the limit, it'll look pretty much like a little square, and so it'll be or a little rectangle. It'll be dr times r d theta, which is that. But the Jacobian determinant is the general way to do the calculation. All right, I'm going to do one more example. I'm not going to compute it all out, but just to show you the spherical polar one that we already did previously for the lectures on spherical coordinates. Remember that in spherical coordinates we had x was equal to r cos theta sine, no, r cos theta cos lambda. I always get it wrong. Y was r cos theta sine lambda, and z was equal to r sine, not d theta phi. We use phi for latitude. You get rid of the thetas and put the phis. All right, that was our coordinates, or spherical polar coordinates. And if the volume element dv, right, was just dx, dy, dz in Cartesian coordinates. And if I want to go to polar coordinates, or spherical coordinates, sorry, it would be d, x, y, and z, d, r, phi, and lambda. And I can evaluate all these partial derivatives, the Jacobian matrix. So let's do it. J is equal to, so dx dr is cos phi cos lambda. Dx d phi is minus r sine phi cos lambda. And dx d lambda is minus r cos phi sine lambda. Then derivatives for y. dy dr is cos phi sine lambda. Dy d phi is minus r sine phi sine lambda. And dy d lambda is r cos phi cos lambda. And finally, the derivatives for z. dz dr is sine phi. dz d phi is r cos phi. And dz d lambda is just 0. And now if you evaluate that determinant, you can find out what this quantity is. And I'm not going to reevaluate the determinant. We've done it before. The determinant turns out to be, I think, oh, sorry, I forgot here. Here, I have to put the d phi, sorry, dr, d phi, d lambda. And we do one more thing that I should point out when we do the integrations is we put the absolute value. Because this determinant is has a sign, right? Because it's the oriented volume. So in this case, we'll put the absolute value, and this works out to be r cosine of phi dr d phi d lambda, sorry, r squared. Yeah. So this matrix here works out to be r squared cos phi, the determinant of it. And you can check now that this has the right units, right? D phi and d lambda have no dimensions, but dr has dimensions of length. R squared is dimension of length squared, so the whole thing is length cubed. So that's another application of these Jacobian determinants in doing integrals. All right, so now we're going to do a little bit more of calculus and linear algebra together. So I'm going to do an example. Suppose we have a function, big X, which is itself a function of little x and little y, and another variable, big Y, which is a function of little x and little y. All right? Now, if I want to take the partial derivative of x with respect to y, and the big X and the big Y variables with respect to the little x and y, I can write that Jacobian determinant is going to be dx y d little x little y, that determinant, and it will be equal to the determinant of big X, little x, big X, little y, big Y, big Y, little x, big Y, little y, and then I can multiply that out. I'm not going to do it, but you could multiply this times this minus this times that. Okay, so that would be the Jacobian determinant changing variables going from the big variables to the small variables. Now, let's suppose we have yet another coordinate system. All right, so this new one is little x is equal to little x of u and v, and little y is little y of u and v. All right, and we're going to try to do the change of variables from big X to little x, and from little x to little u and v, and little y to little y of u and v. All right, so we can do that change of variables. We can do it using matrix multiplication, and it will be the same as the chain rule. So first I'll do it by the chain rule, the usual way. So if I now write x, I want x as a function of u and v, that's going to be x, big X, of little x of u and v, and little y of u and v. That's x, and then same thing for big Y, little x of u and v, and little y of little u and little v. All right, so if I now try to take the derivative of x, d big X, d little u, that's going to be big X, d little x, d little x, d little u, plus, right, x is also a function of little y, and little y times little u. That's the chain rule. And the same thing for y, I would do b big Y, little u is big Y, little x, little u, plus big Y, little y, little y, little u. And I can also do the big X with respect to v, right? d big X, little v, dx, 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 dv, plus dx, dy, dy, dv. And finally, the big Y with respect to v, dv is dx, dy, d little x, d little x, d little v, plus y, little y, little y, little v. So I compute all these derivatives using the chain rule. And if I organize them into the Jacobian matrix, what I get is the following. I get is the Jacobian is right, dx, du, dx, dv, dy, du, dy, dv. And if I take the determinant of that, no, I don't want to take the determinant yet. I just want to do this matrix, that Jacobian matrix. But I want to show that this is equal to the original, the one of the big X with respect to the little x and the little y, and the big Y, little x, big Y, little y, times the Jacobian of going from, so this is the big variables to little variables, times the Jacobian to go for the little x and y to the u and v. So dx, du, dx, dv, and dy, d little u, dy, d little v. And my claim is that if I multiply these out, I will get these ones expressed over here. So let's multiply it out and see what we get. What I get is dx 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 du, x d little x, d little u, this times this, plus this times this, plus d big X, little y, little u. And then let's do another element. Let's do the one that goes here, this times this. So that's big X, little x, dx dv, and plus d big X, d little y, dy dv. And I can keep going. I could do the one down here, that would be this times that. So that's big Y, little x, little u, plus big Y, d little u, and let's do the last one. D big Y, d little x, this times that, times dx dv, plus d big Y, d little y, dy dv. And if we check now, right, this element should be equal to dx du. So let's compare this to dx du. We have d big X, d little x du, plus d big X dy, d little y du. And let's check another term. Let's check this one. So this one element is dx dv, and so this should be equal to dx dv, this one. So that's big X with respect to little x with respect to v, plus big X dy, little y, little v. And the other two are the same, work also. So that means that this, the chain rule for multivariate calculus boils down to a matrix multiplication of the Jacobians. All right, so we can, to go from big X and big Y to little x, little y, and from little x, little y to little u, little v, we can just multiply the two Jacobian matrices. All right, so why is that useful? Well, now I'll show you why. If I try to do the Jacobian determinant, right, d big X and big Y and v, that's the determinant from x to little x, right? So big X and Y to little variables, little x and little y. And then we can go from the little x, little y to the little u, little v variables, x and y and u and v, right? Because this is the matrix multiplication I just showed you a little while ago. This is the determinant of the first matrix. This is determinant of the second matrix. And here I get the determinant of the change from x to u. And so that's a useful identity because we can write it like this. We can, if I divide this by this scalar, what I get is that d x y, d little x, little y, is equal to d big X and y, d little u and v, all divided by d little x, y, du, and v. So this is useful because if I have certain variables x and y, and I want to introduce the variables u and v, then I can simply, by the chain rule, just expand the numerator as a partial with respect to u and v, and the denominator as a partial with respect to u and v. This is a v here. And we're going to use that identity when we do the thermodynamics in a little bit. All right, one more thing that I forgot to mention about these Jacobians, determinants, is when we take the partial derivative, what's being held fixed. So if I had, again, the variables big X is big X and little y, and big Y is big Y, little x, little y, and I take this Jacobian, that is equal to d big X, d little x, holding y fixed, times big X, sorry, big Y with little y, no, let's see, big X dx, yeah, big Y little y, holding x fixed, minus big X little y, holding x fixed, and big X little x, sorry, big Y, jeez, big Y little x, holding y fixed. All right, so these are the variables that are being held fixed in these partial derivatives. So when I take a partial with respect to the little x, I hold little y fixed, and conversely, when I take a partial with respect to little y, I hold the little x fixed. So, all right, a few more useful properties of these Jacobian determinants. So suppose I have d big X, big Y, little x, and little y. If I interchange the two variables at the top, that is the same as interchanging the rows, and so I would flip the sign. So in the determinant, so this would be equal to minus y and x, d little x, d little y. And similarly, if I was to interchange two variables on the bottom, then I would also flip the sign. So we have x, y, d, y, x. So I flip the sign because interchanging two of the bottom variables is like interchanging two columns. And of course, if I interchange both, then I'm going to get the minus sign will appear twice and go away. So if I did y and x and little y and little x, then there would be no sign change between these two. All right, so that's a useful property that we'll use when we do the thermodynamic relations. All right, so let's put those last two rules together to do another example. Suppose I have the partial of x and y, the big variables on the top, and at the bottom I have a little variable x and big X. All right, and I want to evaluate that. Well, the first thing we'll do is we'll interchange the first two rows of the determinant by interchanging the top two variables. So this will become minus partial y x over partial x and big X. And my claim is that this is now equal to minus, and I can just get rid of the big X's, is minus dy d little x. Okay, so that whenever you have a variable that appears in the numerator and the denominator at the last entry, then you can just take it out and you have whatever's left over for your Jacobian determinants. And so I want to show that explicitly, so I'm going to expand out this quantity. It's minus dy d little x holding big X fixed times d big X holding little x fixed minus makes it a plus big Y big X holding little x fixed times big X little x holding big X fixed. And this now is equal to minus d big Y little x holding x fixed. Dx is going to be just 1, so that's 1. And over here I have big Y big X holding little x fixed, that's fine. But here I have partial derivative of big X with respect to little x holding the big X fixed, so this is just 0. And so I get what I had over here, this one, which is in fact holding little x fixed. What? How can I have a holding little x fixed? Sorry, that's big X. That's the big X. And this is the big X. Yeah. All right, so this is all the facts about Jacobian determinants that you need to derive all the thermodynamic relations you need from the Gibbs function. And we'll get. All right, now let's derive some thermodynamic relations from the Gibbs function. So the first thing we'll do is we'll compute the adiabatic lapse rate from the Gibbs function. And so what's the adiabatic lapse rate? It's the change in the temperature of a water parcel as you compress it adiabatically, so without exchanging salt and without changing its entropy. So the adiabatic lapse rate is dt, the pressure holding the entropy and the salinity fixed. And we use this all the time in oceanography because when water parcels travel in the ocean, they, to first order, they get advected around adiabatically and without changing their salinity. So we want to use this quantity. So, but now we want to compute it from our Gibbs function, from the TEOS-10 equation of state, the Gibbs equation of state. So we want to convert this partial derivative here with t with respect to p into derivatives involving the Gibbs function. So the first thing we're going to do is we're going to express this as a Jacobian determinant, right? So this can be written as t eta with respect to p and eta. So why can we do that? Well, this is the partial t with respect to p, and I just explained a little bit that if you have the repeated variable at the end, then you can just get rid of it and you get dp dt, dp holding the last one fixed. So that's the first step. The next step is to remember that the Gibbs function for seawater is a function, well, I could have added the salinity in here also, but to make the derivation simple, I'm going to take it for granted that salinity is constant and imagine that my Gibbs function is not a function of salinity. So we're going to hold it constant anyways. So I'm just to keep the extra step out having to repeat the s at the top and the bottom. Okay, so the equation of state, the Gibbs function is a function of pressure, temperature, and salinity, right? These three variables that we can measure in the ocean, which is why the Gibbs function is useful. So we want to introduce these variables into this Jacobian determinant. And what we're going to do is use the chain rule, and we're going to bring it in on the top, right? T and P, and on the bottom. So we've now expressed, and that is also correct, right, from the chain rule. I've derived that rule before. And the next thing we're going to do is, since there's a repeated variable, we're going to move the t's to the end on the top. So I'll have d, eta, and t. Since I interchange the two top elements, that's like interchanging two rows, so I get a minus sign. Then on the bottom, I will also interchange the t and the p, and that'll give me a plus sign because I flipped again. And then on the bottom, I have repeated variable the p, so this time I'll just interchange the two top variables, the two rows of the Jacobian, of the determinant. So this will become d, eta, and p, and d, t, and p, and since I did only one interchange, I get a minus sign. Alright, so now I could get rid of the t partials on the numerator because they're repeated on the top and the bottom. So this becomes d eta dp on the top, and on the bottom becomes d eta dt with a minus sign. Alright, so then now the last step is to remember that the entropy can be expressed in terms of the Gibbs function as minus dg dt. Right, we derived that in the first video on the TEOS-10 equation of state. So now we can substitute eta for this quantity in both upper and lower partials. So what we're left with is, on the top, is minus minus makes it a plus eta, and there's going to be two partials, one with respect to p, one with respect to t. So I'll write those as subscripts just to make the notation neater. So the subscript means a partial, mixed partial with respect to t and p. So it's a second derivative and it's the mixed one. And on the bottom, I will get eta with respect to t and t twice. So it's the second t derivative partial. And then I have a minus sign, so the whole thing is minus. Oh, that should be g. Sorry, that was g. Right. And that is how you write the adiabatic lapse rate in terms of the Gibbs function. So it's the negative of the second derivative mixed tp of the Gibbs function in the numerator divided by the Gibbs function partial with respect to t twice in the denominator. So we can use the high order polynomial that the physical chemists and physicists have fit for pure water and seawater, and we can take those partial derivatives in that denominator and we can evaluate what the adiabatic lapse rate is in the ocean. All right, second example of relating a physical property of seawater to the Gibbs function. And this one we're going to use is the speed of sound. So the speed of sound in seawater, we'll derive this later, but for now, we'll just take it as a given that it's dp d rho at constant eta and salinity, but let's assume that the salinity is a constant, so at constant entropy. So this is supposed to be, oh, this is actually not the speed of sound, this is the speed of sound squared. All right, so doesn't look like the speed of sound. It's got pressure and density, so sort of feels like it could be. But let's first check the units of this thing, make sure it gives us the dimension of a speed squared. So check that the dimensions of this are correct to be a speed squared. So dimensions of pressure is a force per unit area, that's the kilograms, times acceleration for the force per unit area, and that's kilograms over meters per second squared. That's the units of P. And then the units of density is going to be kilograms per meter cubed. And if I take the ratio, P over rho, what I get is kilograms over meters second squared divided by the dimensions of rho, which is going to be meters cubed over kilograms. Once I take the reciprocal, the kilograms go away, and I'm left with the meters. This meter goes away, and meters squared per second squared. And sure enough, that's a speed squared. So at least it doesn't prove that this is the right expression for the speed of sound in seawater, but at least it's plausible because it has the correct units of being the speed of sound squared. Okay, now we want to express this in terms of the Gibbs potential. All right, so let's do that. So the first thing is we'll write this as a Jacobian determinant. So that's d, p, and eta, d, rho, and eta, where we've introduced the variable that we're holding constant. And now we're going to introduce the variables that appear in the Gibbs function. So this is d, p, and eta over d, p, and temperature, assuming that salinity is held fixed, so I don't have to make the expressions too big. And then the denominator, d, rho, and eta, d, p, and t. And now the top one, I could interchange these two to put the pressure at the end, and these two to put the pressure at the end, and then get rid of the pressure, and I'll just get partial eta, partial t, and the pressure will be gone, and the minus sign I get from interchanging the rows and the minus sign from interchanging the columns will go away, and so the numerator, is just going to be d eta dt, and the denominator is going to be, this time we have no repeated variables, so I just have to expand out the Jacobian determinant. So that's d rho, dp, d eta, dt, minus d rho, dt, d eta, dp. And now to introduce the Gibbs function, we could use the fact that we've already expressed eta in terms of the Gibbs function, right? Remember, eta is minus dg, the temperature. And similarly, we've also done the density, right? Rho is nu to the minus 1 is equal to dg dp to the minus 1. And we can substitute those expressions in here to have everything expressed in terms of partial derivatives of the Gibbs function. So what we get is the numerator will become the second derivative of eta with the minus with respect to t, right? Oh, not eta, g, sorry. Right, I'm going to replace eta by dg dt. So I get a minus g dt in the numerator. in the denominator, I will get d rho dp is going to be the derivative of this with respect to p. So let's calculate that. So d rho dp is going to be minus dg dp to the minus 2 times the derivative of the inside, yeah, g pp. And that's the chain rule. And then what other ones do I have? I have d rho dt. d rho dt is going to be minus dg dp to the minus 2. And then I will have g pt, that cross derivative. And so if I substitute this in here, what I get is, for this term, d eta dt, that becomes gtt with a minus, so I get minus gtt, and d rho dp is gpp with this factor coming out front. So I'll put that factor out at the end, dg dp to the minus 2. And then for this one, I have a minus, and d rho dt, I get another minus, makes it a plus, and it becomes a gpt, and then d eta dp becomes gpt, so another one, and then I have a minus. Do I have too many minuses? Feels like I have too many minuses. Let's see. Oh, yeah, I have one extra over here, right? Because I get a minus sign from d eta dt by plugging in this one here. So that's one minus. Then from this one I get another minus, so this should have been a plus. All right. And then remember that's c squared, right? So therefore, c is going to be the square root of gtt, the second derivative of g, and in the denominator, I'll get the mixed derivative, pt of the Gibbs function, minus gtt gpp. Right, so I put the minus on the bottom and interchanged, so I get a plus here and a minus here. And then I have this factor, right? So if I take this has a minus 2 power, so that goes up in the numerator. And then since I take the square root, the 2 also goes away, so this just becomes dg dp, or just g sub p. C is equals to g sub p. So this messy expression here is how you would express the speed of sound in seawater in terms of the Gibbs function. So it's the partial with respect to p times the square root of the second partial of g with respect to t, and then the second partial is with the, oh, there's a square here. This thing here is a square. And then the product of the two second derivatives with respect to t and with respect to p. All right, so I think that's enough derivations for the equation of state in using the Gibbs functions. I think in practice what people do is they'll just use the TEOS toolbox, and all these partials and all these quantities have already been computed in a toolbox, so you don't have to worry about it. And so if you found this lecture sort of rough going, don't sweat it. You don't have to understand all this. You can just simply know that it's doable. And if you're interested, then you can try some problems and try it out. But I think that's all I have on this. I'm going to go and do some examples in Julia where we'll use the equation of state of seawater, the Gibbs function, and some data, some temperature and salinity profiles in the vertical, and calculate the speed of sound as a function of depth, and also maybe the adiabatic lapse rate.